So let's begin by considering first the observed phenomenon of unimodality. Now, ratios of successive terms turn out to be very useful for the binomial. And therefore, that leads us to consider whether the same strategy might be effective here. Let's try. So let's consider the ratio of two successive terms of the Poisson distribution. Notice I'm keeping the parameter lambda hidden now because it's going to be fixed for the duration of the slide. So look at P of k divided by P of k minus 1. Well, P of k exactly is the Poisson probability up on the right of your screen. To get P of k minus 1, all we do is replace k by k minus 1 in that expression and simply write down the answer. And now we've got a ratio of two Poisson probabilities. An examination of the ratio shows that there are several terms in common. The e to the power minus lambda term cancels the numerator and denominator. Various powers of lambda will cancel, and various terms in the factorial product will also cancel. And when the dust settles, all that remains is lambda in the numerator and k in the denominator. That's going to be hard to imagine a simpler form for such a ratio. Now, what can we conclude from this expression? Remember, we are trying to show that the distribution has a unimodal character for any choice of that hidden parameter lambda. Now, if that is the case, then we first expect the probabilities to increase and then to decrease. If the ratio of successive terms is to be bigger than 1, in other words, if you're on the rising edge of the distribution, then that means that lambda over k must be bigger than 1, and therefore we conclude immediately that pk is going to be larger than the previous term, p of k minus 1, precisely when lambda is larger than k. Or, another way of saying this, the Poisson probabilities P of k increase when k is less than lambda and then decrease thereafter. In other words, they achieve a maximum value at an integer just below lambda. Excellent. Now, before we go on, we should take a little bit of time to look at the expression we've discovered and see if there's any more information that we can milk from it. So let's take a good look at the ratio we've discovered. A little smidgen of algebra will do the trick. So we've got a ratio P of k over P of k minus 1 is lambda over k. Let's clear the denominators by simply cross-multiplying. Multiply both sides by k, multiply both sides by P of k minus 1, and then we discover the fundamental Poisson identity. K times P of k is always equal to lambda times P of k minus 1. Of course, the moment we've got such an identity, we realize that this identity is valid for all non-negative integers k, and therefore, if we replace k by k minus 1, the identity will hold valid. And if we replace k by k minus 1 throughout, on the left-hand side, we'll get another identity of the form k minus 1 times P of k minus 1, and on the right, we'll get lambda of P of k minus 2. Of course, we can generate any number of identities by simple manipulations like this. Now, this is the key identity characterizing the Poisson. Let's see if we can derive simple identities from this basic understanding. Now, recall that we considered k squared times the binomial probability in the case of the binomial. This turned out to be useful. Let's preempt our need and consider an expression like this: k squared times a Poisson probability for some fixed lambda. Can we find an alternative expression for this in terms of other Poisson probabilities? Pause the lecture for a moment and see if, following the lines of discovery that we followed for the binomial, whether you can simplify this and find an expression in terms of P of k minus 1 and P of k minus 2. Restart the lecture when you are ready. we want to find an alternative expression for k squared times p of k. Our basic Poisson identity gives us an identity for k times p of k in red lettering on the top of your screen. Therefore, if we look at k squared and we decompose it into a product of k times k, that brings us into an expression of the form for which we have an identity. Let's exploit this without further ado. Right? Split up k squared and then group 1k with the p of k and take 1k outside the round brackets. Now, once you have this, we have immediate and fertile ground for utilizing our Poisson identity. Replace k times p of k by lambda times p of k minus 1, and immediately we obtain a new expression on the right, k times lambda times p of k minus 1. Well, let's rearrange terms of the product in the front, take the lambda outside, the k inside, and focus again on, this time, k times p of k minus 1. Our second Poisson identity for k minus 1 times p of k minus 1 suggests that if we had, instead of k minus 1 in front of the p of k minus 1, then we'd have a ready-made identity we could use. Well, naturally enough, we start with the expression for k and write it as k minus 1 plus 1. Put this back into our expression and simply regrouped terms. Okay, now the expression is getting cumbersome. It's getting longer and longer, but there is, of course, a method in the madness. Observe that the first term inside the big round brackets gives you k minus 1 times p of k minus 1. The second term is just a Poisson probability evaluated at k minus 1. For the first term, we've got now the second of the Poisson identities we could use. Replace k minus 1 times p of k minus 1 by lambda times p of k minus 2. And now we're almost there. Simply resimplify, pull terms together, and we've got ultimately the expression at hand. Lambda squared times p of k minus 2 plus lambda times p of k minus 1. Now, a casual listener looking at this will say, well, look, you started with a compact expression, k squared times p of k on the left. And then you've created this rather monstrously long expression. Have we really made progress, or have we made things messier? The key here is that the multiplying factor k squared has now vanished. And on the right, we simply have constants, lambda squared and lambda, multiplying Poisson probabilities. And the key here is going to be simply that normalization says that if we just sum over all possible values for k, on the left we have what appears to be an inscrutable expression, but on the right the Poisson probabilities all will add to 1, and this will magically and gloriously simplify expressions.